Okay, so I tried giving this presentation at UGIC and the slides didn't work, the video didn't work. So I wasn't able to show the slides and we were short on time, really rushed, so it wasn't quite the experience that I'd hoped to give and the information that I wanted to share. So I am now recording this after the fact as if I were presenting it live. So I'm not going to do any crazy editing, anything like that. You're just getting raw Jake. So here we go. I want to talk about commitment issues, or understanding Git for better version control and collaboration. Now, Git means a lot of different things. You have to understand Linus Torvalds wrote Git. He's the guy who started the whole Linux kernel program, and he has a way of naming things after himself, and he feels like he's Git, so thus it is named Git. But it isn't just an unpleasant person. Git is an incredibly powerful program. Now, I want you to think if you've ever baked bread or a cake or anything like that. Have you ever wished it had an undo button? You get it in the oven, you think, oh crap, I forgot the yeast, or oh man, I didn't put the sugar in, this is going to taste awful. I wish I could just go undo and get back to that point in time and then move forward. Well, Git basically gives you that control. Git is the master of undos. It's the master of version history. You can undo just about anything as long as you've committed it into your repository. Git branching also allows you to always have a known good copy to work with. So you always know you've got a known good copy and you can go off and experiment in a branch, but you can always come back and keep going. So you can experiment without fear. You can try new things without fear. Git also enables very complex collaborations. You can have two people working on a single code base. They can be working on the same file, and Git will help you merge those changes together without having to sit there and have two people sitting next to each other. Okay, copy paste this over. None of that. It also allows you to share your code really easily. You can go get code from anybody as long as they've committed it to a repository, pull it down and work on it yourself. Really powerful stuff. So what can you store in Git? You can store just about anything. Git by nature, by design, works on text files. So it's going to look at things line by line. But you can store binary files, you can store images. This presentation is in Git. So you can store just about anything. Now, a lot of people, when they think Git, they really start to panic, or they've tried one or two things, but then something goes wrong and they don't know what to do, so they just abort. I say a lot of people because this has been me for a long time. Git is powerful, and to be powerful, it has to be complex. There's the scratching the surface that works, I don't know, 75% of the time, but when it doesn't, it gets really complex and a lot of people just bail out. You know, in the presentation I asked, okay, who's used Git? A bunch of people raise their hands. Who's used Git and has given up on Git? And a lot of those people kept their hands up. So what I want to go over today is kind of peek beneath the covers, peek under the hood, so that you understand what's going on in Git, so that when you then say, oh my gosh, something happened, I'm going to go Google it, and people start saying things, you're not going to be like, this is all Greek. I don't understand what he's saying. I don't understand what he's doing. So that you can hopefully then understand, oh, it's really just simple. It's this, 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 and this. I know what state my file is in, and I can pull it back. So don't panic. We're going to go through this. I love this. I love XKCD. I love this, right? The ultimate don't panic is if you ever want to try something in Git, but you're not sure what it's going to do, just make a copy of your folder, name it backup, and then you can do whatever you want on your folder, on your main folder. And if that breaks something and you can't figure out, just delete that, rename your backup back to your normal file, and you're off to the races again, because Git stores it all there within that file. So let's lay a foundation. Let's really understand what's going on underneath the hood. So to do that, we need to talk about the basic units of Git. The first are blobs and trees. When you commit a file to Git, it creates a blob. It takes that text file or whatever, puts it in a super compressed format, very useful for moving it around, but it's not very human readable. It tracks the relationship of those files using trees. You can think of trees as directories. So you have your folder, it's got a couple different blobs in it. That's kind of how Git stores files internally. Now the next unit is a commit. And a commit is a snapshot in time with an ancestry. So every time you make a commit in Git, it takes a snapshot of all the files and folders in your directory, what we'll call the working tree, we'll get to that in a second, and makes that snapshot. So when you do it again, it's going to snapshot it. Even if the file hasn't changed, that is going to be part of that snapshot. This means you can always go back and find the state of your program or your folder or your project or whatever at that given commit. So once you've made a snapshot, it's very hard to lose it. So these snapshots, like I said, they have all the blobs and trees associated with your working directory. Also has a commit message. It has a lineage, so it knows who its previous commit was, and it has author, timestamp, all sorts of other metadata associated with that commit so that you can look back through the history and figure out, okay, what happened, what did I do? So now that we've got commits, which are chained together as lineages or ancestries, we're going to name them. And this is a branch. A branch is a history or a lineage of commits with a name. And that lets us easily refer back to it, and we can then start to branch off so that one commit may have two children, and we'll go over this later, and then we can do a lot of really cool things with merging. This is where the power of Git comes into play. Now the important thing to remember here is that a branch is just a pointer to a commit. So branches are cheap. It's just a single pointer. All the commits are already stored. It's not duplicating. When you create a branch, it's not duplicating a bunch of commits here and a bunch of commits there. It's all one big group of commits, and you're just putting a label on different commits within that whole ancestry tree. Now finally, it all comes up into the repository. It's the collection of all the branches, all the commits, all these different objects, these basic units we've been talking about. And it's stored in the .git folder. When you create a repository, if you show hidden folders, you'll see a .git. So you've got commits, which are made up of blobs and trees. Those commits chain together to create branches, and all your different branches, all the different commits live inside a repository. So that's the basic structure. Now repositories, going one level up, can be cloned. Git is distributed. That means there is no one true source of truth. Like on a server, there's no one repository that's the master and then everything else comes off of that. It's distributed. So every time you clone a repository, you have the full version of that repository. You've got all the history, you've got everything. So that means if my computer crashes and I can't get to my repository, but I cloned it somewhere else, I can just pick up right where I left off. This makes Git very powerful, and it also allows you to, by tracking these different remote repositories, allows you to do some really cool things that we'll talk about later. So I want to talk a moment about hashes and immutability. Every commit has what we call the SHA-1 hash. A hash is a mathematical operation that you feed it a bunch of data, it crunches it all and gives you a number that is almost always guaranteed to be unique. For all intents and purposes, it is unique. If you want to dive into the nitty-gritty, there have been collisions, but for all intents and purposes, that's unique. So every commit gets a unique hash, a unique ID. And this is important because commits never change. So that unique ID will always refer to that one commit. What goes into the hash for the commit? The data itself, all the blobs and trees, the author and committer info, name and email, timestamps, and the ID of the parent commit. So this means if you ever do a commit, if you ever create a commit, you can never then create that exact same commit again. And this is what allows Git to do its whole history thing and gives you a lot of assurance that you know exactly what commit we're talking about here. So another important thing to remember is that commits are almost never deleted. They may be hidden, like when you delete a branch, suddenly they don't show up when you say, hey, show me all the commits in the history, but they're still there, most likely. Some garbage collection can happen. But usually a commit doesn't go away unless you intentionally get rid of it. So if you delete a branch or something, oh no, I just deleted the branch, I didn't want to do that. Chances are you can get it back. Almost everything in Git is reversible. So key takeaway here with all these hashes and stuff, commits are never modified. Once you make a commit, you can't go back and change that in place. You can create a new commit that contains the same blobs, the same files, but it's going to have a different timestamp. It may have a different parent, so it'll be a different commit. So the content may be almost the same, but the commit itself is different. And that is very important as we dive into branching, rebasing, merging, that sort of stuff. So just remember this. Commits are never modified. They can be, I won't say copied because that makes it sound like you can have the identical. They can be almost identical, but they're never modified. So to really understand Git, we need to talk about the 4 storage areas that Git uses to do all its work and keep track of changes. So these are the working directory, the index, head, and the repository. So the repository is, like I mentioned earlier, it's the .git folder. It's all the blobs, all the trees, all the commits, everything as super condensed binary files formatted for transferring over the network, right? The staging area, also referred to as the index, is your proposed next commit to the repository. This has all the files that you say, okay, I'm done editing this file. I'm going to stage it. I'm going to put it in the index, ready to work on, or ready to be committed. Working directory, or the working tree, is basically your current commit, deblob, decompress into a folder structure that you can view in Windows or Linux or Mac or whatever. It's your working directory. This is where you're making your edits. And so that's where you're going to be spending a lot of your time. Finally, head is just a pointer to the currently checked out branch. And this allows you to track where you are and when you branch, where you go. So when you check out the project or check out a branch, you decompress that commit from the repository to your working directory. You make changes in your working directory. You stage those changes up to the index or the staging area, and then maybe you do some more edits and you stage those. And then once you've got all your work staged and indexed and ready, then you write a commit message and commit it up to the repository. So from the repository to the working directory, stage to the index, commit to the repository. That's the basic workflow there. Now, the consequence of this is that the same file can exist in all 3 areas with different content. So if we go back here, the repository could contain version 1 of your file. The index could contain version 2, some changes you made and then staged, and then you could have made more edits, and these could be version 3 in your working directory. Now, what this means is if you don't go through that workflow and commit it, and you do certain operations, it may go so you make those operations, and then you check out a new branch or you do some other stuff. You may find that some of these areas don't look the way you expected. So it's really important to understand these 3 different areas and how files move between them. And we'll go through some examples here. So let's talk about the basic Git operations. What do you do day in, day out when you're operating on Git? So let's talk about the life of a file. A file in Git can have multiple statuses. So when you first create a file in your working tree, your working directory, it is untracked. Git doesn't know about it. Git only knows about files that you tell it to follow, to track. And a note here, Git will always do what you tell it and only what you tell it. You may not understand what you're telling it to do, but it will only do what you tell it to do. And this is true of computers in general, usually. So if something's happening that you don't understand, this just means that you need to look in and understand exactly what you're telling it to do a little bit more. So we've got the file, and let's say we commit it, and now it is unmodified. Git knows it's tracking it, but it's now unmodified. So we can edit the file, and now Git says, hey, we edit and save it. Git says, hey, I'm tracking this file, and in the working directory, it's different from what I've got in the repository. So I'm going to flag that as edited. Actually, I think it's different from what's in stage, what's in the index. So it's, hey, this is modified. Or from an unmodified file, you can remove it, and then that doesn't necessarily delete it. When you git remove, it just says, hey Git, don't bother tracking this file anymore, and it'll just live there in your working tree. This can be dangerous because if you do things that blow away your working tree, that file could get blown away. So just know untracked files can be lost. So once you've modified it, then we're going to stage the file, which moves it into the index. And then when we commit it, the status goes to unmodified and the file gets put in the repository. So that's the basic life cycle of a file. So let's go over committing. Committing is really the bedrock operation. So our starting point here, we've got version 1 that was committed, and now we want to make some edits to version 1. So we make those edits in our working tree, our working directory. Now we have version 2 of the file in that working tree. We stage our edits with git add, and that moves that new copy or that new version into the index. Then we commit it with git commit, and that moves the index, or that moves that version of the file up into our repository. You see it advances head to that commit, and also advances the branch to that commit as well. So if we look over here, head and master still point to version 1, but now head and master point to version 2. So that's the basic cycle of performing edits. You do it in the working directory, stage it to the index, commit it to the repository. So let's look at that in action here real quick. I have this branch called main, and what I'm in right now is I'm in Virtual Studio Code, and this is a wonderful extension called Git Graph. This helps me visualize what's happening in Git. It's really powerful. Really helps me follow exactly what I should be doing here. So let's look at file 1, and I've got some lyrics here from one of my favorite songs, The Boxer by Paul Simon. So, well, I've also got some stuff from Iraq. So let's say Feeling Groovy. So I've edited it, and you'll see, if I look here, I'm in file1.txt. It is, VS Code isn't giving me any markers to say, hey, there's something different here going on. It just says, hey, this is unmodified. But if I save this, you'll see that it adds an M. Hey, this file has been modified. If I go to my source tree view, see I've got modified here. So I'm going to now stage my changes. So I just hit plus, and now file 1, this new version, has been moved to the index. And I have the chance to add a message. And now I'm going to commit that change. And so now that new version of the file, actually not just that version, a snapshot of that whole repository, of that whole working directory, has been added as a commit to, I'm in the main branch, so you can see there's my commit, and its parent commit was this one called Popo. We'll see that here in a second. And so on and so forth. So that's how you modify stage, and commit a file here in Virtual Studio Code. Now, as I mentioned before, branching is a really powerful feature in Virtual Studio Code. And remember, branches are cheap. They're practically free. Don't be nervous about using them. And branches just allow you to say, from this commit, I want to come over here and work on some different stuff. You'll just have a new commit with the same parent as another branch or another commit, and then you can go off and do whatever you'd like. And if you want to switch between branches, you check out that commit or that branch. And what a checkout does is it replaces the content in the working tree, index, and head with the last commit in the checked out branch. So what does that look like? So right now I'm in main, and you see file 1 has this content. But if I go here and check out my merge branch, suddenly that line disappeared. My working directory was modified, my index was modified, and the currently checked out commit head was also modified. And if you look at my graph here, you can see I've got a couple different branches coming off of this commit called customers. I've got this rebase branch, I've got this merge conflict branch, and I've got main that continues on. Now, one of the difficult things with visualization here is that this makes it look like whatever is here on the left is kind of the main branch, the one that everything should come to. And I want you to more think about it like every branch comes off as a Y. There is no one branch that is technically more important than the other. All branches are technically equal. It's up to you as the programmer, as the writer, as the user to assign branches that priority. Now, one of the most common branch workflows is to always keep your main branch as the known good copy. You never edit main. You just saw me do it, but I rarely ever edit main. I'll usually create a dev branch where I can go and do anything I want to my heart's content with it, and always know that if something goes wrong, I can always go back to main, and that'll be good. If you're using something to deploy your code, either to like PyPy or it's a website and it gets deployed up and is a live website, that could always point to main so that in this one repository, you could always be working with whatever it is you're doing, trying all sorts of crazy things, sure in the knowledge that your users are always going to see a known good copy. So that's one of the more efficient ways to use branching. So what do we do when we've done all this work in our branch? Okay, yeah, this is good. This is what I want it to look like. Now let's pull it back in. This is where we have a merge. So the most simple merge is a fast forward. So let's say we're working on the master branch. We then started working on this issue 53 branch, but in the meantime we had to do a quick hot fix to fix something in our master branch at the same time. So we create a new branch called hotfix, we do a commit, and now hotfix is one commit ahead of master. Well, we are going to merge master into hotfix with a fast forward. Or when we do that, Git says, hey, I can tell that the commit you're on is just the simple child of the commit before, or there's a simple clean one-to-one lineage all the way back. So I don't have to do anything fancy. I can just move master forward and Bob's your uncle. So fast forward, it is what it says, just really quick and easy. It doesn't even create a new commit. It just moves master forward. But what if it's not so simple? So we go back to issue 53, we do some more work, that becomes commit 5, but now we want to merge our work on issue 53 back into that main branch. Well, when we do a merge, Git will go back, look at the common ancestor, and then try to mash all the files together, all the changes since that last common ancestor into one file. And most times it works just great. And you get a new commit with that new updated snapshot of your work as a new commit, and then it moves master forward. So you can see that the commit 6, our new commit at the head of master, has two ancestors, C4 and C5. So if I want to track the history, I need to go look at both what happened in C4 and what happened in C5 and C3 before I get back to that unified history, C2 and beyond. Now, conflict, like in life, is inevitable. What happens if, when it tries to mash those two files together, it determines that, hey, C4 had this line saying this, C5 had this line saying something different. Git isn't omniscient. It doesn't know which one you want to choose. So it's going to pause the merge and say, hey, time out, I found a conflict. I'm going to insert some lines into your file to mark where that conflict is, and then it's up to you as the user to go in, edit that file to be whatever it is you want it to be, to make the decision as you, the creator, of what that end state should be. Then you're going to save that file, you're going to commit that as a new commit, and then I will continue the merge process. So what does that look like? Oops. So I went ahead and made this merge conflict branch. And if we look at this, I'm going to check out main here real quick. If we come back here and we look at what this commit changed, you can see the real lyrics are 1 step ahead of the shoe shine, 2 steps away from the county line, just trying to keep the customer satisfied. I went ahead in main and changed that to 1 step ahead of the popo. You know, I'm hip that way, right? I'm very hip. Don't ask. But in my merge conflict branch, I came in here and I said, actually, I'm going to change that to 1 foot ahead of the shoe shine, 2 feet away from the county line. That makes a little more sense, and I don't sound, my 12-year-old nephew, I'm sure, is just rolling his eyes at me somewhere right now. So I have changed that one line, this line 6, 2 different ways. So when I come here and I say I want to merge this branch, I go to main and I say merge conflict into main. I'm going to create a new commit. No, I want to fast forward. I don't want to squash the commits. That I'll explain later. So we'll just create this. And it says error, unable to merge branch. It found that merge conflict. It's telling us to fix conflicts and then commit the result. So what Git did, what Git did is it gave me a version of that file with both versions of those 2 lines that it's saying, hey, I don't know what to do. And it marks it with these comments here, all these arrows and head, and then this is the divider, and then everything between that and these other arrows, merge conflict. So this is what is in head, which right now is master, and this is what is in merge conflict, the branch I'm trying to pull into merge. Now my job is to go in and edit this text file. This is just a text file, and make those lines be what I want them to be. Now VS Code has some really great tools. It sees those markers, because those markers are the same every time, and says, hey, I recognize this as Git saying there's a conflict. I'm going to give you some one-click buttons to say, you know what, I don't want popo, I want 1 foot ahead of the shoe shine. So I'm going to accept the incoming change here in blue. And you see it gets rid of those lines. I could have easily, just as easily, gone in here and said, nope, delete that, okay, and there it is. And now I'm going to save it. And when I save that, I then need to stage it, and it's kind of giving me this commit message already, but I'm going to say something to remember it by, and then I'm going to commit it. And then Git said, oh, okay, everything looks good. I'm going to go ahead and finish the merge. And you can see I now have this new commit that is the name of it has the commit message that I just gave it, and I've merged conflict into main. So now that I've done that merge, I can actually go here and just delete that branch. And bye-bye. Now, I need to do something here real quick. Ignore this really quick. Explain this later. Oh no, it is set. Okay. Okay, so you can see that that commit is still showing up because it's part of that lineage now. This commit has two ancestors. It has this one and this one. And you can see where I've done some other work as well. So that is how you handle a merge commit. So now that we've got the basics of Git, that you commit files, you create branches, you do your work, then you merge them together. Now let's talk about GitHub. GitHub is basically a Git server in the cloud so that you can do those remote operations with a bunch of collaboration tools tacked on to make life really simple for when you're working together as a team. Now remember, I said Git is distributed. You can have multiple copies of the repo in different locations. And when you clone a repository, what it does is it keeps track of where you cloned it from in this thing it calls a remote. By default, the name is origin, but you can name it whatever the heck you want. Once we've got this remote, that basically establishes a link to say, hey, I came from here, or I want to follow this remote repository. So I'm going to I'm going to follow that so that I can track the changes between the two. There are three common operations. There's fetch. That says I'm tracking the remote I'm going to call origin, and I'm going to download all the commits from that remote that are not in my local repository. It's not going to apply them, it's just going to download them so that I have them. Now, after you've done a fetch, you can then merge, let's see, how does it work? You can merge the commits from the origins branch into your local branch, and there could be named the same name, usually are the branches. And so that is basically you saying, okay, a bunch of work has been done remotely. I'm going to pull that into mine before I then start continuing my local work. This is such a common operation, this fetch then merge, that we have a second operation called pull, and that just says fetch and merge and move forward. Usually it's just a fast forward. If you have done work on your local copy and somebody else has done work on remote and you save it and then you try and pull and there are conflicts, that's when it can get a little nasty and you have to do conflict resolution, do those merge commits to make sure that Git knows exactly what you wanted to do. For this reason, I always do a fetch or do a pull before you start working locally. This is especially important if you're working as part of a team. This just always ensures that that is clean. You're not going to run into these conflicts. The other operation here, we've pulled data down from the remote. What do we do if we've made commits and we want to push that or send that up to the remote, up to GitHub? We do a push. That says take all the commits that are in my local but aren't in the remote and send them on up. And depending on the setup on your remote server, it may automatically do that fast forward merge. So that's the idea here. You have a local copy of a remote. It is set to track a remote copy or a local copy of your repository. It is set to track a remote copy, and you can basically sync your commits between the two copies. So when we work with GitHub, this is kind of the basic GitHub development model. This is how I develop. This is how a lot of people develop. Rather than create your repository locally, you're first going to create your repo on GitHub. Then you're going to clone it down to your local machine. You're going to create a local branch to work on and do all your commits, do all your work on that local branch. Then you're going to push your branch up to GitHub. You're going to do a pull request on GitHub, and we'll go over pull requests here in a second. But once everything looks good, you're going to do the merge in GitHub to merge your branch that you did your work on in that's now in GitHub to GitHub's main. Then you're going to go to your local main. You're going to pull the changes that occurred that you did but are now in GitHub down to your machine, and that will advance your main to match GitHub's main, and then you're going to delete the local branch. Now, I know what you're saying. This is a lot of extra work. Why am I going through all this confusion? Well, it's mainly for that pull request. The pull request in GitHub is a very powerful thing. It allows you to work with others to say, hey, I've done something. I'd love to get your eyes on it. I'd love to get a review. GitHub also has actions that you can do on a pull request so that it'll run all your tests and put a limit that says, hey, I won't do a pull request because your tests aren't passing. So let's go look at some pull requests here. This is a library that I've been working on. You may have seen it, Pallet Jack. I've done a couple different presentations on it. But here are all the closed pull requests. There's a lot of bumps here and dependencies, but here's a pull request I've done. Here are the different commits that are part of that pull request. I requested a review. Steve left a comment. Everything looks good, so he approved it. And then I merged that branch into main, deleted that branch. You can see I was working on the dev branch, and then I can go back. This is a great way to document your progress, get a second pair of eyes on it. You can also see here in actions, we have a bunch of actions set up that every time we do a pull request, it runs all my unit tests. So I can verify that all my tests passed and everything's working great. Our website is also a Git repository. So here is pull request. It's open. This is a draft pull request. So you're saying, hey, I'm doing some work, not ready for review yet. But you can say, it's done a bunch of checks and saying, hey, guess what? This isn't deploying properly, so you can't merge this yet because it's broken. And this is a safeguard against, so that we always have that known good main branch always working. So pull requests are a very powerful tool in GitHub. Issue tracking is another powerful collaboration tool in GitHub. If we go over to issues, this is our bug tracker basically, right? We can track bugs that we see. We can add enhancements that we want to see. We can basically do whatever we want. So let's go back to Pallet Jack here. You can see I've got a bug. I've got some enhancements. I've opened a bunch of these. Steve's opened a bunch. Anybody can open an issue in this repository. So this gives you a way to collaborate and send feedback back to the maintainer, or if you're the maintainer, basically gives you a place to say, hey, this would be a really great idea. I don't have time to do that right now. I'm neck deep in 5 other projects. I'm just going to create an enhancement and get back to it when I can. So you can see I've got a lot to get back to. These often end up pretty deep. But yeah, so that's issue tracking. So what happens if you see somebody else's code, you think, oh, that's really great. I've got an idea that I could submit to you, but I don't have write access to your repository because I'm not going to give you write access to mine. You can just blow away whatever I've done. Now, I could usually get it back, but I don't want you, quote unquote, stepping on my toes like that. So what you can do in GitHub is fork a repository. And if we go here, if we're just looking at the repository, you can see this little fork button. And what that would do is it would basically clone that repository to my own GitHub account and set the AGRC pallet jack repository as its origin. And then I could go clone a copy of my fork locally, make my edits, push them up to my GitHub, and then open a pull request between my copy in GitHub and this copy in GitHub. And that would give me, the main developer of Pallet Jack, a chance to look over your proposed edits and say, oh yeah, that's a really great idea. Let's go ahead and incorporate, or that's beyond the scope of what I want this to do, or dude, none of your tests are passing, go back, try again, right? I'm sure that, yeah, no. It basically gives anybody a chance to work on it. In the open source world, forking is everything, right? If you don't like a project, you can just fork it and continue on your own. Doesn't always mean you'll have success, but technically the capability is always there. So that's the main advantages and a lot of what you'll be using in GitHub. Pull requests, issue trackers, forking, there's project management, there's documentation, there's a bunch of other stuff in GitHub that we didn't cover. But it's a really powerful tool for working together in teams. So for this last bit, I want to talk a little bit about advanced Git topics, rebasing, resetting, and recovering from errors or lost data. So rebase, you'll see this often. A lot of people will rebase instead of merge. You might say, okay, so what's the difference? Rebase is basically rewriting history. So if we look at our commit history here, we've got our master branch and we've got an experiment branch. Now, what if I say, okay, yeah, experiments worked, but rather than come off as a child of commit 2, I want my parent to be commit 3. That's what rebase. I'm moving the base commit for that commit. But remember, commits are immutable. I can't change that parent. I can't change the parent commit without changing the hash. So what a rebase does is it actually creates a clone, a copy, an almost copy of that commit. We're going to call it C4 prime, and then hides the original commit C4. It's still going to be there for a while, but it's hidden. So now experiment is off C3, and what this gives you is a nice, clean, linear history. So this is why a lot of people will rebase and merge rather than doing a merge commit. So what we had here is we had a branch, we did some work, the work was great, we said, okay, we're going to rebase our work back onto master, and then we're going to merge our work into master, but because it's a nice long linear history, it just does a fast forward. So now we have this nice long clean linear history without a bunch of branches coming off. So what does that look like in Git? Well, if I open Pallet Jack here, show you my development history. You can see I don't have a bunch of branches coming off, even though each one of these releases was a merge of new work. You can see this is a very clean linear history. You can look through this and know exactly what changed at each snapshot. Otherwise, you would have something like what we have going here, where it's coming out, coming in. You're like, okay, did this get added here or here? It's all right there. So it's up to you whether you rebase or merge. Generally, as long as you can ensure that nobody else has done something between the time you made your edits and you want to merge and rebase and merge, you can go ahead and rebase. There are a lot of things written online about that difference, so I encourage you to look it up and see what the difference is. But if you follow that GitHub development model that I talked about earlier, where you're using pull requests in GitHub, you can usually always do a rebase and merge. And it keeps your history nice and clean and committed. Okay. There's also the option to just cherry pick. Let's say you've done some work on a client or on a different branch, and you won't say, well, that snapshot right there has some really good stuff in it that I want to pull into master right away. I don't want to wait to merge all of that. Well, I can then cherry pick that commit, and that basically says just take that one commit, not the whole commit history, not the whole snapshot, not the latest one, just that one snapshot, and tack that on to the end of master. So it's an easy way to say, oh, that one commit had a lot of good changes that I like, I'm going to pull that in. So commit cherry pick can be useful in rare cases, but it can be useful. So finally, the one that confuses a lot of people and can get you in a lot of headaches if you don't understand what's happening is reset. Now you can think of git reset as the ultimate control Z. I want to go back to some previous state. I just want to change where I'm at. I want to go back. There are 3 different types of resets: soft, mixed, and hard. And the difference is what it does to those 3 areas that we talked about earlier: the working directory, the index head, and the repository, 4 main areas. Sorry. So when you do a soft reset, it just moves head back a commit, but leaves everything else the same. So the edits you just made and committed and now are resetting, they're still staged and ready to be committed. They still show up in your working directory, but they're not in the branch, or the branch is not pointing to that commit, as you can see here. So moves the branch back, but leaves your edits ready to be recommitted if you want. A mixed, which is the default, moves the branch back, but it also unstages your edits. This basically reverts your working directory, or leaves your working directory with your new edits, but reverts all of Git back to before. Finally, the nuclear option is a hard reset. This moves the branch back, it unstages your edits, and it removes them from the working directory. Now, this is one of the places where you can lose data. If you had made changes to your working directory and you hadn't committed them and you did a hard reset, those changes are gone. There's no getting them back. So you always want to be very careful when you do a git reset, when you do a hard reset. But understanding these 3 different areas and that life cycle of a commit is very important for understanding git reset. So which reset should I use? If you want to just completely abandon your current line of work, pretend like it never happened, you can do a hard reset. Or what you could do is check out one of the commits and create a new branch at that point and just continue from that point, and then you leave the rest of those commits just dangling. Now, what if you've got, let's see, you don't have any work in progress, you don't want anything to keep, you just want to point your branch at a different commit. You do a hard reset. Wipes out everything. What if you did a commit and you want to go back and change something about your edits, but you don't want to add an extra commit for whatever reason? You just want to go back and stage some new stuff, maybe change the commit message. You can do a mixed. That will take your old edits, it'll leave them in the index, you can add new stuff, do whatever, and you're off to the races. So let's say you did a commit, but you're like, oh, I need to go do these edits and add those, or I want to change my commit message. That's when you would do a soft. Confusingly, Git has this git commit amend, which will quote unquote amend the last commit. Now, remember what I said earlier. Commits are immutable. You can't actually amend or change your last commit. What that does is it does a soft reset. So it moves it back, and then you do another commit, and that original commit is just left dangling. It's still there, but it's hidden. Now, recovery. Let's say you've deleted a branch, but you're like, oh wait, I didn't merge, I wanted that branch, what's happening? Commits are always there, except when they're garbage collected or you intentionally delete them. But they're very loyal friends, they're always there. The git ref log, not reflog. I always thought, you know, no. Git ref log tells you what happened on the current branch. And if I go to git graph and I change my settings to say include commits mentioned by ref logs true, suddenly you can see new things showing up. And this was a branch that I merged in. You can see 49th Street, call me Al, right there. Or that was a branch I deleted. The commits are still there. They're just not referenced by any currently named branch, or they're not in the history of any currently named branch. So with that setting done, let's go back to Pallet Jack. Reload. And suddenly you're going to see all the different branches. You know, each one of these was a branch that I did a merge commit, or excuse me, a pull request on, and did a rebase and merge. But it's because I did a rebase, these specific commits are not in my main history. Now you can see from review mainly save GDB. Oh, right there. And that one's right there. They're the same content, but you can see they're different commit hashes. So they're copies of that commit because I did a rebase. These commits are still there. If I wanted to go back to this commit, I could. You can see, like, okay, it looks like I can go back about a year. Oh, no, I can go back further. Git does do some automatic garbage collection. I haven't been able to really nail down when it does that, but there's a lot of garbage collection that can occur. So you can see there's a lot of stuff here that if I wanted to go back to some of these branches, I could. So if you do something, as long as it has been committed, you can get it back. It may take you some time, but you can get it back. So remember, commit is your friend. So, final word of advice. Help, I committed a password. You've put something in a repository, maybe you send it up to GitHub and you're like, no, they shouldn't be able to see that. How do I get rid of it? You have to go through and basically delete all the old commits that reference that, or that had that content in them, and create new commits with all that history, but without that that line or that file. There is a tool called Git Filter Repo that will do all that for you. Go check that out if you ever get to that point. To help you with that, or to help you avoid that, Git has what it calls the .gitignore folder. .gitignore says files matching these patterns should never be added to the repository. So you can see I have my secrets file where I store passwords, usernames, that sort of stuff in my gitignore, so that I'm not going to show you it, but where is secrets? I don't have a secrets in this. If I did have a secrets, it would show up kind of grayed out here. The GitHub default has a bunch of other stuff so that you're not like loading like DS store files or any of these other weird things. It helps keep your repo clean, and it helps you avoid committing data that you don't want to commit, files you don't want to commit. So that's a pattern I highly encourage you to use. Put all your secrets in a certain file, and then make sure that file is in your .gitignore. So that's been a lot. If this were the presentation, they would have waved me off about 15 minutes ago, but since it's not, hey, you guys get an hour-long video. Resources. All the images that I've used in this presentation come from the Git book. Now the Git book is available as a book, but it is also at git-scm.com/book. This is the main Git website. This is in the documentation. This is, I'm going to nerd out here, but this is a great read. I didn't really understand Git until I sat down and read through this to prepare for this presentation. I had a basic understanding of what was happening, but I didn't really understand Git until I read this. And it is written so that you can come into Git without a lot of prior knowledge, but a willingness to learn and learn it. A lot of great stuff in here. So check that out. There's also the reference, so all the different commands, everything's in there so you know exactly what's happening. Other resources, Stack Exchange is your friend, man. How do I do X in Git? Somebody's asked that already in Stack Exchange, and there's going to be 5 different answers telling you how to do it. There are a lot of great tutorials on Git on both YouTube, and if you're fortunate enough to have access to Pluralsight, there's some great courses on Pluralsight that are basically video versions of that Git book. You can just dive right in and get it all. So, here we are. Thanks for your attention. No questions because I'm not in front of a live audience. I'm standing in my office, but thanks for paying attention, and feel free to reach out to me. You can reach me at jdadams@utah.gov or UGRC, we're at gis.utah.gov. Come check us out. Huge shout out to my coworkers for being patient with me with Git and helping me understand what I'm doing. So with that, have a fantastic day.